You know? Okay, this is question number 29. I gotta shrink this a little bit because I can't see it. So I have a remote control. This is a table here. This is a table. On the table we have a remote control sitting like this on the edge of the table. And the person is going to push down on the remote control with the force F. Now let's give you a few things about the remote control. This remote control has a mass of 0.142 kilogram. 0.142. The length of it, the length of the remote control is 25 centimeters. That's a good size remote control. That's the size of this. You know? That's a big remote control. Okay, old-fashioned one. Rest on the table as shown in the figure with the length L. Oh, L is overhanging. So the overhang is called L. So this portion from here to the edge of this is labeled L. To operate the power button on the remote control, it requires a force of F equals 0.350. You know if you push hard, what's going to happen to that remote control? It's going to flip over and land on the ground. How far can the remote control extend beyond the edge of the table? What is L? Find L and still not tip over when you press the power button. Now the one assumption we have to make is assume that the mass of the remote control uniformly, which means in the middle of it. So it's uniform. Assumption, assume the remote control is uniform. What else? Also assume that the button is 1.3 centimeters or 3.1 centimeters from the edge, the overhang edge. So that's what we have. Let's look at the remote control and see what we have. If you picture the remote control, this is my remote control. I'm going to make it a little bit bigger. Oh. The length of it is 25 centimeters. So this is the 0 centimeter. This is the 25 centimeters, right? That's the remote control. I can make it a little bit wider if you want to make it look like a remote control. Here we go, like this. And we can have fun, put like buttons on it. Little circle, button, up and down, power button, shut off, whatever. That's the remote control. Yeah. First thing we know, we have a force pushing down of right here. It's pushing down. That's you pushing to turn on. So I'm going to put the force down like this. That's F, which is 0.350. And it is located where? At the distance 1.31 centimeter. What else we know? We know the weight of the remote control, since it's uniform, has to be where? At 12 and a half, halfway through, right? And the weight is the mass of it. We know the mass, 0.142. We know gravity, which is what? 9.8. And that number will be what? Uh, 0.142 times 9.8. 1.39, is it? Okay, what else do we know? 25 centimeter long. The other part we know, it was hanging at right there, L away from the table. Well, when you push down on it, what is that corner table? That corner piece is going to do what with it? Push up on it. And where? At L, right? At L. That distance from here to there has to be whatever that distance, which is L. This has to push up. That's the normal force, whatever you want to call it. The table pushing up on it. And they don't really care about that force, because if you look at it, if it's not flipping, if the thing doesn't flip, we know all the forces pointing down should equal all the forces pointing up. Down we have the 0.350 plus the 1.39, and what's pointing up is the normal. Can we find what that normal force is? I don't care for it. They're not asking for it, but I'll put it there. 1.74. Remember that remote control is not spinning. It's not moving. Which means what? We have static equilibrium. Sum of the forces to the left equals right. Do we have left and right here? No. What's the third equation then? Remember, when you have static equilibrium, there are three conditions. Sum of the forces, condition 1, the net force in the y direction is 0, which means up equals down. The second one, the net force in the x direction is equal to 0, that's right equals left. We don't have right and left here, so I don't have to look at that. And what's the third one? Sum of the torque is 0. Pick any point on that remote control and do the torque, it should be 0. And let me pick this point for the torque, where n is the normal. Pick that point. This one. I could have picked this point. I could have picked any point. I decided to choose that one. Probably be easier if I pick the 0. But I already said that point in terms like in your head figuring what the distance is. So if I pick that point, that means the normal force is gone. I don't have to do it. It's over. There's 0 torque for it. It goes through that point. The only two forces going to make the remote control spin is this one and that one. If the surface of the table is missing, just you only have this rod here, just that leg there, the weight of this is going to make it spin which way? Clockwise, right? Clockwise, is that negative or positive torque? Negative. So negative, the force, which is 1.39, times the distance from here to here. Well, what is the distance from here to here?
We don't know that though.
Well, we know the distance from here to there is L,
Yeah.
right, Jen? We know from here to there is 12 and a half. So that should be what? I can leave it in centimeter, by the way. I'll be okay. 12.5 minus L. From here to there is 12 and a half. From here to there is L. So from here to there is the difference between them. This one is going to make it spin which way? Counterclockwise, that's positive. The force, which is 0.350. And what is the distance from here to there?
L minus 1.31.
Perfect. L minus 1.31. The whole thing is L, this is 1.31. Equals to 0. How many unknowns do you see in that equation? One unknown. So let's go through the math. And my L here is going to be in centimeter because I left it in centimeter. 1.39 times 12.5. That's 17.375 minus plus 1.39 L plus 0.350 L minus 0.350 times 1.31, 0.459. Subtract, add these two numbers together. I'll put on the next page. These numbers both negative. If you add them and move them to the right side, they become positive, right? So this plus this I got 17.8 if I round that to 3 significant digits equals, let's add these numbers. 5 and 9, 14. 1, 3, 4, that's 7. 1.74 L. Can we get what L is? Divided by 1.74. I get 10.2 centimeters. .2 centimeter. So let me go back and type in 10.2 centimeter and say submit. Good. I have 10.3 rounding. I never round. When I write the numbers here, I carry all the digits. They gave me the credit, but it says significant figure feedback. Your answer is 10.2 was either round up differently or used a different number of significant figures. L equals 10.3. Now notice, actually, maybe I'll do this. If I pick this point for a pivot point, I might have made life a little bit easier on you. Because if I use that point, your answer is not going to change. If I use this for a pivot point, this one's going to make it spin clockwise. That's a negative 0.350 times the distance, which is what? 1.31. From here to there is 1.31. This is going to make it spin counterclockwise. That's positive. We know what n is, 1.74. Times the distance from here to there, which is what? L. And this would be minus 1.39 times 12.5. Does that make the math a little bit easier? Probably. 1.74 L. Multiply these numbers, move them to the right side. Let's see if that number is 17.8. Ready to test it to see? .350 times 1.31, add to it 1.39 times 12.5 equals 17.8335. See that? 17.8. What is L equal to? 10.3. If you do 17.8, probably if I use, because I left all the digits there, let's see, 17.8 divided by 1.74, 10.2 actually, not 3, 10.2 really, 10.229. They said I got a different number than them, significant digit, I still got the 2. Oh, maybe because I know why. Because I rounded that answer. If I carried all the digits, let's see, 0.350 times 1.31 plus 1.39 times 12.5, 17.8335. I didn't use the 335. Divided by 1.74, still 10.249. So it's 2. I don't know how to get the 3 there. But you could have picked any point. I think in terms of the math, it would be easier if I picked that point here. The only reason I don't like that, which means you had to go and find what n is. But it's not that difficult to find, and it didn't take us that long. Now, if you don't want to find n, if you don't want to do this, then what I did here is perfect, because I don't have to know what n is. Just do this one. Let's look at 33. Okay. 33. A uniform metal rod with the mass of 0.36 kilogram, length of 1.1 meter, is attached to a wall by a hinge, a horizontal wire pulled to the wall. So the way the story is, because you have a horizontal wire, the only way that could happen, this is the wall here. That's the wall here. The rod must have been like this. We have a rod attached like this. There's a horizontal wire. The wire must have been looking like this, holding it from falling. So it can't be horizontal, because if the rod is horizontal, this is the rod, the wire will not be horizontal. A uniform metal rod with the mass of 3.6 kilogram. The mass of this, 3.6 kilogram. And a length of 1.1 meter. Is attached to a wall by a hinge. So there's a hinge here, let's say like a pivot point here, and there's a screw in it holding it, so that rod can move up and down freely at the base. A horizontal wire bolted to the wall 0.38 meters above the base. So this height here, 0.38 meters. Above the base. I don't know why they give us the angle. We can calculate the angle. This angle here is 25. That's silly to give us the angle. Oh, 20, I'm sorry. 20, not 25. Because if I'm going to plug in the answers in the back of the book, on the software, I need to make sure the numbers are correct. So this angle is 20. Above the horizontal. The wire is attached to the top of the rod. Okay. Find the tension in the wire. That's the first part. So what is the tension here? Find T. That's part A. The second part, it says, you know what? This wall is pushing on that in this direction. F of X. Find T. Find F of X for part B. The horizontal component they wanted. Find the vertical component, the wall. Now, I'm not sure if the wall is going to be pushing up or down. What do you know? Do you have any idea? Up or down? You want to make it pushing up? It's an assumption. I know it's going to push down, but we'll see. Let's say I make it push up. It's going to be a negative value. We'll call it F W. I don't know. Let me call them, because I use F of X and F Y somewhere else. Let's call this, instead of F of X, let's call this what? F A? Just to be different. Because I'm going to say sum of the force in the X direction is 0. F of X, you're going to get confused. So I'll call it F A. It's called F of A. I can call them F of A and F of B. It really doesn't matter. F1, F2, it doesn't matter what I call them for labels. So that's what we're looking for. The first thing, actually, when I saw the problem, I says, why are they giving us the angle? It's silly. Isn't this angle the same as this? Well, we can find that angle. The sine of this angle, the side that's opposite, divided by the hypotenuse. We have both sides. So I'm not sure why they give us the 20. We could have found it. Shut up. I forgot to put on vibrate. We can find that angle. Notice if that was not given to us, like if the angle is not given, I would have said, I call this theta, and I would have said sine of theta is equal to the side that's opposite, which is what? 0.38, divided by the hypotenuse, which is what? 1.1. Theta will have to be what? The inverse sine Let's see if that number is 20. Again, this step you don't have to do it here because they're giving you the angle. But if it wasn't given, 20.2. See that? So that's why I wasn't sure like why they gave us the angle there, but because we could have found it. So if you see a problem where the angle is not given, but you are given the side, you can use trig to find it. This is not to solve it, so this is just to prove like there was a waste of time giving us that angle. We could have found it. Or they're just trying to be nice to you. They don't want you to suffer too much. Let me draw the beam, draw the forces on it. The rod here. This is the rod. So we have a force. I drew a force in this direction. I called it FA. We have a force. I drew it upward, FW. We get the tension in this direction. That's T. And what else we have? It says uniform rod, which means the mass or the weight of that is going to be in the center of it. The center of that is halfway through the 1.1. What's halfway through 1.1? What is 1.1 divided by 2? 0.55. So the weight of the rod which equals 3.6 times 9.8. $35.28. How about 35.3? Now here's the little problem. The problem is I know this length. I don't know what that length is. So if I make a triangle out of it, maybe that's why I gave you the 20 degrees. Just they figure there's so many calculations, we'll give you a little break there. You know this is 20. You know this is 0.55. Can you find this value called x? Can you find what that value is? Cosine, right? We use cosine 20 degrees equal the side that's adjacent over the hypotenuse. What's x equal to? 0.55 times the cosine of 20 degrees. .52 roughly. 5168. 52. And we're assuming that that rod is not moving. If that rod is not moving, what does that mean? We have equilibrium, right? Sum of the forces, the net force in the x direction is 0, which means right equals left. What do we have pointing to the right? FA. What do we have pointing to the left? T. Can't solve it. Two unknowns. Huh? What do you know? I think W is going to be correct here. Pointing upward, FW. Number 2, the net force in the y direction has to be 0. Again, that means the forces pointing upward should equal the forces pointing down. What do we have pointing upward? FW. What do we have pointing down? 35.3, right? So now we know what FW is. Let me put that answer in. This is what, 35, two significant digit, 35. Submit. Correct. So we got this one correct, 35. Now we have 2 more answers to answer. So the third condition, what? Sum of the torque equals 0. Again, the easiest spot to pick there, you pick the spot with the most forces on it. Unknown forces. And the spot with the most unknown forces is this spot, right here. Because if you pick that value, the torque by this one is 0, the torque by that one is 0. So this is going to create torque. Remember, you're always looking for the force times the distance that's perpendicular to it. So the distance here will be what? X. So this will make it spin which way? Clockwise. That's a negative torque. Negative the weight, which is 35.3, times the distance from here to there. And that's x, which is 0.52. Let me extend this a little bit so you get to see the picture. This is T. T is going this way, right? So I need to find that distance for T. The T is going to make it spin counterclockwise. That becomes what? Positive. Times the distance. What distance? That's this distance. And what is that distance given to us in the problem? That's 0.38. Can you see it right here? How many unknowns do you see there? 1. 0.38 T equals 0.52 times 35.3, 18.4 divided by 0.38. T equals 48.3. It says find T, 2 significant digit. What's that answer? 48, right? Submit. Perfect.
Can you just go over why you're using the 0.38 value
Why?
for T? Like that distance?
Oh, because for the torque you always want to find the distance from the force to the pivot point, but it has to be 90-degree angle distance. So the only 90-degree angle
Right, okay.
is this distance from here to there, John, because you want that angle to be 90. Just like when I did this, I couldn't use that distance.
Right, you have to use the X distance.
If I want to use this distance, I got to find that component of the force.
Okay.
I don't want to start finding components for just like if I want to use this distance, I got to find the component of this that goes in that direction, straight up there.
Okay.
So either you do that or you find the distance that's perpendicular to the force.
Okay, thank you.
You're welcome. So now the last one is what's FA? We know FA equals what? T? Now plug it in. And that's 48. Perfect. And that was number 33. $35. Number 35. A 75-kilogram person stands on a uniform 5.6 kilogram ladder. So here's what we have. We have a ladder leaning against a house. There's the ladder. Okay. We have a 75 kilogram person standing on the ladder. So this is the person. 75 kilogram. The ladder is 5.8 kilogram. So the mass of the ladder is 5.8 kilogram. Uniform ladder, which means the weight is going to be a point in the center of that. The length of the ladder is 4 meters. And they have a picture for us. And the ladder happened to be going as height is 3.8 meters to the peak here. That distance 3.8 meters. This is 4 meters here. The floor is rough, because if it's rough, it's going to have forces on it, and the picture they've given us, there are forces on the floor. They said there's a force pulling in this direction to keep you from skidding, and they label that F of 2. There's also a force pushing up there. They label that F of 1. The wall on the other side is frictionless, which means there's no forces up and down. Doesn't slide. Nothing there. But it has one horizontal. And they call that force what? F of 3. It's pushing in that direction of F3. Find F1, F2, and F3. Now, the only other thing we need to know where the lady's standing. And they've given us that. It says the lady, if you draw her weight down, it is the distance from here to there that was given in the picture is 0.7 meters. 0.7, I think so, yep. Let's clean it. Too much stuff, too much junk on it. This is my ladder. I have F2 in this direction. I have F1 is going up. Notice this one didn't give us the angle. We have to calculate the angle. We know the weight of the ladder is going to be straight down. The weight of the ladder, which is what? The mass of the ladder, 5.8 times 9.8. $36.84. How about 36.8? We have the weight of the person, which is 75 times 9.8. $735.
For the weight, 5.8 times 9.8, I got 57.
You did?
Yeah.
I'm sure, yeah. Mine sounds wrong, actually,
Yeah.
because that's almost 6. 5.8 times 9.8, 56.8?
Yeah.
56. I said, what, 36?
Yeah.
Yeah, 50. Thank you. Tough being old. 56.8. More coffee, too. what else we got? F3, pushing in that direction. One little problem is, I know that distance here. From this point, I know this distance is what? 0.7 meters from this inch. They gave me that. But what about that distance? How far this point from this point? Does anyone know? We need to find it. I know my ladder is 4 meters long, so I know this piece is 2 meters. I need to know what this distance. That means I need to know what theta is here. If I know what theta is, I'm in good shape. If I go to my bigger triangle, can I find theta? Let's look at sine of theta. This is the big triangle right there. Let me get a purple mark or a yellow mark. Do I have one of them? Yeah, right here. Here's my big triangle. I don't know if you can see it when I highlight it. Does it show up?
Yeah, fine.
Like that. Sine of theta is the side that's opposite over what? The hypotenuse. Do we know what the side that's opposite? 3.8. Do we know what the hypotenuse is? 4. What is theta? The inverse sine of 3.8 over 4. Second sine (71.8 degrees). So now, can I find what x here, that distance x? We know this is 71.8. I can use the cosine. Cosine 71.8 equals x over 2, multiplied by 2. Take the cosine times the 2. Is it 0.62? So this is 0.62 meters. And now we apply the 3 conditions. First condition, the net force in the y direction is 0, or x direction, doesn't matter which one you write first. Again, that means up equals down. Up is what? F1. Down is what? I get the 56.8 plus what? 735. 56.8 plus 735. 791.8 or 792. This is find F1 using 2 significant digits. 2 significant digits, that's what? 790. Submit. Oh. Says my number is not correct. F1, I'm just looking at my numbers here, just making sure I didn't write anything wrong. 70 kilogram. Is 5.8 or 5.6? 5.8, yep. And 70 kilogram. Let's double check the numbers. Oh, 70 kilogram, not 75. My mistake, sorry. So I'll leave this. I'll do it, I won't change the note, but if that was 70, I'll show you the answer is correct, because I said 75. If that was 70, that number will be what? 70 times 9.8, which will be 686. Add to it 56.8. That'll be 740. Let's see if the 740 is correct. Yes. So now my numbers now I'm going to match, so I'll do the math because I used the wrong weight here. Math 70 instead of 75 instead of 70. I see 75. I don't know, it says 70 there. I don't see where the 5 coming from, but I must have wrote.
For F1.
This is F1 up there. Is that what you're asking, Dominic? Yeah. Let's do number 2. Sum of the forces in the x direction is 0. That means right equals left. And right equals left, what do we have? Right is what? F2, and left is what? F3. I don't know what either one is. I'll come back to it. F2 equals F3, okay. And the next one is the torque. The net torque is equal to 0. I'm going to pick that pivot point that kills F1, F2. So now let's see. Looking at the weight of the ladder itself is going to make it spin which way? Clockwise, that's a negative 56.8 times the distance from here to there, which is 0.62. Minus the weight of the person, which is, I have what, 735? Minus, because that's clockwise, times the distance from here to there, that's 0.70. And just like the other one, John, I gotta look for that distance now going this way. What's that distance that's perpendicular to that force?
You
don't have to, it's given to us. You could, but it's given to us. See it? The distance from right to there is 0.38. 3.8.
Yeah.
You could do it, calculate it, but we have that value. So that would be what? Positive F3 times 3.8. And how many unknowns do you see there? 1.
Now how do you, oh, because F3 is going to the left, you would just say that's counterclockwise.
Correct. Now you pull in that direction is going to make it go counter. So 56.8 times 0.62, add to it 735 times 0.70. This is equal to 549.7, which means F3 is going to be 144.7, how about 145? If it's 145, what's F2? Since F3 equals F2? So we get F1, we get F2, we get F3. We got them all.
I think the first one wasn't working because we have to convert newtons to K Newton, I think.
Oh, the one kilonewton?
Yeah.
Yep.
That's what was screwing me up on this one.
If they want it in kilonewton, that's 0.79 or 0.74, depends what number you're using, you know?
Yeah. So all I do is put a decimal.
Are they all in kilonewton?
Yeah.
I couldn't test mine just because I
Oh,
used
yeah,
the wrong
now-
one.
Now it works.
Yep. Yeah, kilonewton. Again, I couldn't test mine. My numbers don't match. And you had one more question, and that's 37. Looks like just from the questions here. I don't have anything from yesterday, collision, that rotational collision, huh?
I don't think it got that far, that's why.
Yeah. High heels or standing on your toes, ballet dancing, whatever. So this is 1137. Forces. So we got your foot here. Let me draw a picture of your foot. I have a picture of it. Oh God. That's, I don't know, under the giant's foot. Huge foot there. I'm looking at the picture we have there. Here we go. We have a force going this direction, labeled as, I think, F heel, I don't know. FH, I'm assuming H for heel, at 59.2. And this is like the ground here. And we have another force in this direction, and that's F1. Now, I don't need to see. We have a scale on the bottom, and it says this is the 0 mark here. This force is the 4.25. And we have a force pushing upward here. It's 223. And the value for that one is 9.66 centimeters. The distance. So they're giving us a distance from the picture. Let me go back and read the questions. Forces in the foot. That's the topic. Showing the figure shows the forces here. Just before she takes off at the start of the race. Somebody's going to be running a race, I guess. Find the magnitude of the force Fy or Fh. Find F of H. Find F of 1, I think. Or they call it J, I think, and I called it 1J, whatever it is. Find F of H, comma, F of J, or 1. I think they call it J1, I can't really tell what it doesn't really matter. F of H and F of 1. There was nothing mentioned about that angle there. You know? this angle here, there's nothing mentioned about it. So I'm looking like if I draw a line through this, like this is your foot here. If I draw the line as this is your foot, does that say it's 90 degrees? I'm looking at it to see what they implied. So if I draw the foot like this, what I see is a force pushing upward right here. That's on your toes of 223 Newton. I see this force FH, but F of H I think is going to be like this at 59.2 degrees. And there's nothing mentioned about f of 1, the angle, so my assumption here really, then it's perpendicular, like this. If there's nothing mentioned about it, we need to know if that angle is perpendicular or not, you know? So this is your foot here, this is that force going up, this is this one, and this one at 59.2. Distance here, this is what? Like if I put the distance right there, mark them. I don't like this problem. Like, it's not stating, I mean, I think I know what they meant. I just don't like the fact they just leave it like we have to guess on what they implied there. This is 0. This is 4.25 centimeters. This is 9.66 centimeters. The only force I don't like is the heel. I don't like that force of the heel. So let me break it down to x and y component. It's going to have a component in the x direction, one in the y direction. So if I look at the heel again, I mean the foot again, I'm going to have this force here going straight upward of 223. This is the distance on the bottom, so we'll leave the distance, the scale. Here's the heel. I'm going to break this into two components. It's going to have a component in this direction. It's going to have a component in that direction. F heel H in the y direction. This is FH in the x direction. I'll come back and put some numbers in it. I can break this component to F heel cosine 59.2, and this is F heel sine 59.2. See, up equals down here. I got a problem with up equals down. Which side is up? Which one is down? What the angle? This angle here. See that? We don't know if that's perpendicular. It's not 90 degrees with this. I don't know what that angle. So it leaves me a little confused there. Like, oh, what am I going to do? That doesn't mean I can't get the answer.
The angle for 59.2 is not based on the foot. It's based on the horizontal. Isn't it?
Yes.
Because if you look at the picture, so it's not based on the way that you drew the free body diagram. It's based on the angle of the foot. It's not. It's based on the horizontal. Because if you look at the picture, I'm looking at the picture in this book. It's drawn based on the horizontal.
Based on the horizontal, okay.
Like here.
Like based on this line here, this one. Based on that line?
Yeah. So if it see how it's based on the horizontal line, so it's not based on the angle. It's based on a horizontal
Okay.
line. So like you have it drawn correctly here, where you have it based on.
So if I do this,
So because it seems like it is using the proper x and y axis, which is why I'm confused. Because then you have to find f and j.
if that's the case, I can get this. No, I'm just curious here. Let me look at the picture again. If I do the okay. Well, okay. You might be right there, so I can change my thinking on that one. It won't change much of the work. 11.37. Here's the foot again. I'll change a little bit. This way. And we have this one going up there, 59.2, right? That's with respect to this horizontal, you're saying, right? That angle?
Yeah.
Okay. 59.2. We got another force in this direction. We have no idea what the angle is. F1. And we got one that's pushing upward, right? Go in that direction, pushing upward, of what, 223? Okay, I can do the same thing here. And we have the distances. Let me use this now as the foot then, this line. If I look at that line there, if that's what they're implying, if you just watch that line here, the horizontal I drew, I have this one here, at angle 59.2, and this is f of h. So that's called f of h, now 59.2, right? Here. That's f of h. I got this one up. Actually, that might make my life a little bit easier in terms of visualizing things. 223. Now I got some force that looks like this. I don't know. f of 1. I know the distance, this is 0. This is 4.25. And this is what? 223, that's 9.66 centimeters. Because the distance written on the bottom. Let me look at it this way then. That's Mike saying, I think that's what they meant. Again, I can still take this force and break it down, and the bottom leave f of 1 alone. I didn't notice any angle on the bottom one, so I'm not sure if there's implying anything. Certain angle, not an angle. Just say I don't like that problem. Just feels like they could have added one more line to the question so you know what they were talking about. This is F heel sine 59.2. This is F heel cosine 59.2. And F1 is down here. I can tell you what the F heel is. Now, if we're not really sure what that angle is, we can give it theta here and break it down to x and y component and figure F1 in the x, F1 in the y. And once we have them, we can find what F1. Notice if I call this angle theta here, because there was nothing mentioned about it, I can break this force here this is going to have a value in this direction. And what is sine of 59.2? Sine of 59.2. 0.86 maybe? And what's the cosine of 59.2? 0.51? Now I can take this value, break it down to a component because it was pointing in this direction. It has one to the left and one to the right. One down, and that's F1 sine of theta. And this will be what? F1 cosine theta. Because I have no idea what that angle is. Now I get them all pointing in the right directions. Let me try the usual 3 steps. Up equals down, left equals right, sum of the torque is 0. There we go. Number 1, equation 1. The net force in the y direction is 0. That means up equals down. What is up? 0.86 h plus what? 223. What's down? F1 sine of theta. Step number 2. X direction is 0. Right equals left. To the right, what do we have? 0.51h. To the left, we have f1 cosine theta. So here we have one equation. I forgot fh. I wrote h here. F of h, right? Not h. We have two equations by how many unknowns? I don't know why I use h. F of h. Oh, I wrote h, so it would be f of h. That's why. Same thing right here, f of h. So you have two equations by how many unknowns? 3. That's not good. Let's do the torque. And the best point to pick here, because if F1 is confusing me, it has a lot of unknowns in it, is you pick this point. Remember, this distance is 0. This is what? 4.25 centimeters away. And this is what? 9.66 centimeters away. So when you do that, this has no torque, this has no torque, this has no torque. The only one's going to make you spin this and that. This one's going to make you spin which way? Counterclockwise. That's positive 223 times the distance from here to there. What's that distance? 9.66 minus 4.25 from here to there. Is that 5.41? It's the distance from here to here. Let's look at this. It's going to make you spin clockwise. That's a negative 0.86 FH times the distance from here to there, which is what? 4.25. So 4.25 times 0.86 equals 3.66 FH equals 223 times 5.41. 1206. What's F of H? 330 roughly. Let's try 330 for F of H. 330. Submit. Ooh. That's the easy one. F of 1 is the hard one. Because I'm really not sure if there's an angle, no angle, and all the stuff. So I just made an assumption there's an angle theta. So I'm going to find F in the x direction, which is this one. I can use one of these equations. Once I know what F of H is, notice if you know what F of H, you plug it in these two equations. See the two equations here? Let F of H 330, so 330 times 0.86, 283, add to it, 223 equals. So 506.8 equals F1 sine of theta. And let's look at this one, 0.51 times 330. It's 168.3 equals F1 cosine of theta. Two equations by two unknowns. Best way to solve them? Divide both of these equations by each other. If you divide them, what will happen to F of 1? What's sine over cosine? tangent theta equals 506.8 divided by 168.3. 3.01 theta equals the inverse tangent. 3.01 71.6 degrees. If you know theta, can you find what F1? Use any one of these equations. Excuse me, 168.3 equals F1 cosine theta, theta 71.6. What's F1 equal to? 168.3 divided by the cosine of 71.6. 533. Let's see if we are right. It doesn't say how many significant digits to use. Every number is 3, so I'll go 533. So we were correct on both answers. And I really didn't know if that, like, there was nothing. Just said, you know, this. I guess that wants to make an assumption. We don't know. My first assumption that this is 90 degree, I thought it was 90 till Mike brought it to my attention. He goes, no, I don't think that's what they meant. You know? So I said, okay, plan B then.